Hello, today we'll be discussing two types of circuits. One's going to be an excitatory circuit and one's going to be inhibitory. So we'll start with the excitatory circuit here. To begin, we'll have three neurons here. The first one will assume an action potential has already traveled down to the axon terminal, causes Ca2 plus calcium cation to come into the cell. So calcium will bind to the synaptotagmin on the vesicles, which will cause the vesicle to translocate to the cell membrane. There will be T snares on the cell membrane, V snares, I'm sorry. No, T snares on the cell membrane and V snares on the vesicle, and those will connect with each other and cause the cell membrane, the vesicular membrane to come together and release the neurotransmitters through exocytosis. Neurotransmitters will enter the synaptic cleft and bind to their receptors. The neurotransmitters here, I'm sorry, are glutamate, their primary excitatory neurotransmitter in the central and peripheral nervous system. So they'll bind to their receptors called AMPA receptors, which are ionotropic receptors. And so the ion that they let in when glutamate binds to them, which when they're activated, is sodium cations. So sodium will flow through these, and if summation is great enough for sodium flowing into these to cause the membrane potential to become positive enough to reach threshold, it'll cause an action potential down this neuron, down the axon. So these sodium gated, voltage gated sodium channels at the nodes of RON-VA and between the myelin sheath coating will cause sodium to go into the cell and calcium to be released eventually. And once sodium travels all the way down to the axon terminal, it'll cause, again, opening of these voltage gated calcium channels, causing an influx of calcium into the cell, where the same thing will happen. It'll bind to synaptotagmin on the vesicles. The V snares and T snares will interlock once the vesicle translocates. It'll fuse the vesicular membrane and the cell membrane, release more neurotransmitters. Here, again, glutamate, primary excitatory neurotransmitter. It'll bind to these AMPA receptors here and cause further excitatory responses in further neurons, causing greater action potentials if summation is great enough. More action potentials, more sodium released down the cell through the nodes of RON-VA. And that's an excitatory circuit. And so the next one's an inhibitory circuit, and the same process happens for the first part of the cell. The only difference is the second neurotransmitter release. So the first neurotransmitter will be glutamate, causes the excitation of the second neuron here. AMPA ionotropic receptors allow Na plus through. Depolarization occurs if it reaches threshold, summation is great enough. Sodium comes through at the axon at the nodes of RON-VA, reaches the axon terminal, apologies. Calcium comes in, binds to synaptotagmin on the vesicle. Only these vesicles here, we'll erase them, they are filled with the primary inhibitory neurotransmitter in the brain, the central nervous system, and the peripheral nervous system, GABA. So GABA will be released in the synaptic cleft by the same process, exocytosis, and it will bind to GABA A receptors. Here are GABA A receptors. And like AMPA, these GABA A receptors are ionotropic, but they allow chloride into the cell, chloride ions. So these are negatively charged ions. So once GABA binds to the receptors, chloride's allowed into the cell. And so the reason why the cell is depolarized by sodium cations is it makes the cell more positive, so the membrane potential comes more positive when it enters. But when chloride enters, it's a negative anion, so it'll hyperpolarize the cell, inhibiting further depolarization. So these sodium-gated channels will not be activated. They'll be inhibited by chloride because it will not reach threshold and become hyperpolarized. It'll become more polarized. It will not reach that threshold of around negative 55 millivolts, as shown here. This is the action potential need to reach. The membrane potential is usually at negative 70, so it'll need to reach negative 55 to cause an action potential, but if it goes lower than negative 70, it'll have no chance of reaching an action potential. So chloride will hyperpolarize this third cell, causing an inhibitory response. No more action potential will be generated, and no further neurons will be contacted by this third neuron. Thank you.